Okay, hi everyone. This is the last video I'm going to be making for test one. And this video is mainly going over some reaction considerations and some synthesis problems, mainly the reaction part. Synthesis we'll try to tackle into. Um, yeah, it's either you get it or you don't, but I'm here to help add to what you do get, hopefully. We just had a UVA game today and we won. Go Hokies. I'm still in my maroon gear, but I think Esme was there, but if you guys were paying attention at the beginning, I think Adam Klump was actually on the court. He was like behind the tables. I don't know why he was there, but I did see him. So Adam was there. Okay, I digress. I'm just going to go ahead and share my screen. Okay. Zoom share. There we go. Now I guess you can see my screen. Okay. So again, this is mainly just to go over some reactions and some reaction considerations, especially with the new stuff we learned. Okay. So if you're struggling trying to keep up, I'm here to help because again, we're not slowing down. After the test, we're going to jump right into spectroscopy. It's going to be a hard left turn to what you're normally learning. So hold on tight. So the thing I want to note is, so on that graph that you have strong activators, moderate activators, weak activators, and then you have weak deactivators, moderate deactivators, and strong deactivators. That entire chart that he gives you that I talked about in the last video, there are two commonalities, and that's your moderate activators and your deactivators, because you have esters, or not just esters, but you have amides as well. So an amide would be like similar to the structure I have right here in the left here, but instead of an O, it would be an N, but they still follow the same rules. So what's special about this is that it constitutes both as an activator and deactivator, because what I'm trying to say is that oxygen has a lone pair. And if you remember, if it has a lone pair, it is orthopair directing because it's going to stabilize resonance in a way that promotes the orthopair position. Not only that, but O, kind of like the O in phenol, but not to the same degree, is an activating group because the O terminus on the ester group right here is one of your moderate activators. Conversely, the carbonyl carbon right here, that is partially positive. That's a partially positive carbon because you have the carbon connected to two oxygens that are pulling electron density away from that. And if you have a partially positive carbon, well, you have basically an electron drain or an electron sink where aromaticities or the electrons in the aromaticity system are being leaked out. All right. It's deactivating that ring. All right. It's partially positive. Right. This is the same stuff that we've been learning. So compared to these two rings, well, I'm going to keep this one here. This one, that's activated, and this one's deactivated. Activated, deactivated. Okay. Activated, deactivated. So what does that mean? Well, if you're to react it, let's say we were to brominate it, Br2 FeBr3. All right, where will it add? Well, if you think about it, which ring would it rather react with, an activated ring or a deactivated ring? Well, kinetically, it will favor the activated ring. So it'll barely react with this ring, and it'll mainly, react with the ring on the left. So this one is favorable. All right. Now that we know that, well, where will it add? Well, if we know that this O terminus is orthopair directing, if you know your chart, the O terminus of the ester is a moderate activating orthopair directing group. Well, it's going to add orthopara. Let me use a different color. Let's use green. Orthopara. You have two ortho spots and you have a para spot. Okay. So if you have these three spots, well, where will it add? Well, out of the three, it'll want to add to the pair group. And the main reason is that oxygen is still sp3 hybridized. All right, that's an sp3 hybridized. It's a tetrahedral shape. Not only that, but while phenol OH is relatively small because it's an oxygen and a hydrogen, well, this is an oxygen and entirely other carbonyl and phenyl group. So it's pretty large. So it's very it's a considerable amount of steric strain. So if you were to add your bromine onto those ortho groups, well, you have a sigma bond right here that's rotating. That's rotating on that axis. Well, remember, this is sp3 hybridized. Oh, come on. sp3 hybridized. And it's spinning all around that axis at a kink. And because of that, the ortho group's not very favored because of steric hindrance. So where will it rather add? Right here. If we were to brominate it, bromine would want to add to the para position of your activated ring. Plain and simple. Okay. Now let's get into some naphthalene. All right. Naphthalene. It is one of your polycyclic aromatic compounds that you do have to know. Well, your three ring in a straight chain for aromatic compound is anthracene. And then you have 4 rings that are kind of bundled up. That's pyrene. And then add a 5th ring to that, you have benzopyrene. You do have to know those. So your 2-ring structure is naphthalene. Naphthalene also looks like this. I just drew the circles for simplicity's sake, but right here, where everything is stabilized by that aromaticity ring. So sp2 hybridized is planar. It's a Huckel number. Okay. So now let's look at this. If I were to react naphthalene, right? Actually, before I react it, let's go ahead and just get some stuff down. So you have your bridgehead carbons right here. Okay. Your bridgehead carbons are important because they don't really want to react at all. Okay. So the carbons right next to it are alpha. I'll say this right now. Whenever you react it with naphthalene, things will want to add to alpha. And I'll show you why in a second. While over here, you have beta positions. Beta positions. You might be thinking, well, why? Well, let's talk about it. So, like I said, things will always want to add to alpha positions generally. So if I were to brominate it, bring back here, let's give some chlorination some love. Na Lewis acid with chlorine. Okay. So if I were to add the electrophile here, right, where here, let me go ahead and draw the hydrogens real quick. So you know that this always has the hydrogens because sp3 hybridized. It has the hydrogens. Well, let's break this double bond. All right, now that we have an electrophile here and then positive charge there, all right, we have, sorry, my roommate's watching something outside. We have a structure that looks like this. And this double bond can break, or not break, excuse me, door hinge over and put the positive charge right here. All right, it's pretty stable. And the general rule with the polycyclic rings is when you react it, you don't really want to disrupt the aromaticity or the aromatic ring of the other compound. All right. It's a lot more favorable to just react or to form resonance structures with adjacent double bonds that are not aromatic. Because the moment we broke this, it's no longer continuous. So we break the aromaticity in that right ring. But still, you get the point. The right ring still has a residual double bond that can stabilize that resonance structure or that positive charge. If we were to add that electrophile over here, all right, the electrophile added here instead, and the positive charge is here, it has nowhere to go. Now you might be thinking, well, that double bond can door hinge over there. Well, you're right, it could, but will it? Not really, because as a general rule, we don't want to break the aromaticity of the other ring. So that resonance structure is not as favorable. We would much rather have the positive charge here and be stabilized by that double bond. So that's why it's more favorable for electrophiles to add to the alpha carbon, generally. All right. Now, with that being said, let's look at the 4 different scenarios. So we already know if you just have a plain naphthalene and you're reacting it with one of your various reactions that you know, I'm just added to an alpha carbon. But what if you already have something there? Well, that's where it gets a little tricky, but still easy to grab or get a hold of that concept. So we have 2 groups right here that I laid out. A nitro group, which is a strong deactivator, and an alcohol group, which is a strong activator, right? So if that's our situation, well, how does that change the rules? Well, it does a lot. So nitro group pulls electron density away from that ring. So the ring that it's on, that's deactivated. All right. So if you were using that, that money system that Dr. Berg taught you, well, that ring would have a value of, well, negative $10. While here you have a non-activated ring, but a not deactivated. It's not deactivated. So while this is like negative $10, this is just $0, right? If you're looking at the monetary value, but it's not deactivated, but still compared to negative 10, well, what would a bromination reaction rather work with? Would it rather react with a normal aromatic ring, or would it want to react with a deactivated ring, which, if you remember, deactivated rings react a lot slower and activated rings react a lot faster. So relatively, the right ring is a lot more favored. So now that we know that the right ring is favorable, where will it add? Well, you only have two options, one of the alpha carbons or one of the beta carbons right here. And we know generally we want to add stuff to the alpha carbon. So the beta carbon we won't really add to. We'll add stuff to the alpha carbon. Now, you might be thinking, top or bottom? Well, if you look at steric hindrance, well, that NO2 group is kind of faced out like this. So if we add another NO2 group, like another nitro group here, that's going to be sterically hindered. Contrastly, if we added something over here, well, now it's not facing the same direction as NO2, and it's just reacted. And it's facing away. So we'd much rather have an electrophile add here. This spot is favored. There's not as much steric hindrance. Now, what if we had something in this position? All right, a relatively meta position from one of your bridgehead carbons. Now, how do we react? Well, the rules still apply. We have a deactivated ring, and then we have a ring that's not deactivated. So which one will want to react? The ring that's not deactivated, because it's a lot more fast. It's faster. Because the right ring, the green ring, has a monetary value of 0, while the ring on the left has a monetary value of negative 10 because it's strongly deactivated. So where will it add? You have 2 alpha positions, and you have 2 beta positions. All right. Well, the answer is, well, it'll add to an alpha carbon, and deactivated root, I'll say that rule at the end. Where will it add? Well, honestly, it's probably going to be a racemic mixture, because this NO2 group's facing away. It doesn't really have a whole lot of steric hindrance. So you might have, like, I don't know, 60% here, 40% here of your product. It's a racemic mixture, most likely. But if you had to pick one, pick the one that's farther away. So I would pick this one if you had to pick anything, because the least relative steric hindrance. But in actuality, it's probably going to be racemic. It's probably going to be hard to control. So if you have a strong deactivator on one ring, whatever you add has to be on an alpha carbon in the other ring. So if you have a deactivated ring, it'll add to the alpha carbon on other ring. I like that in blue. Now let's look at an activated ring. So here you have an activated ring and a normal non-activated ring. All right. So this ring would have a monetary value positive $10. This would have a value of $0. So if you were to add, let's bring back bromination. If we were to brominate it again, where will it add? Well, it'll want to react with the strongly activated ring because it's a lot more favorable. So if we know that whatever we add, whatever we react, will want to react on the same ring as an activator, where will it add? Well, if you remember, your alpha carbons. So here on this left ring, alpha carbon. Where will it add? Well, it can't add on the top alpha carbon because something's already there. So the only spot is this one. That's the only alpha carbon that's left, and it'll add there. Because remember, when we add electrophiles, we want them to add on the alpha carbon, right? So that's where it'll add. Now let's look over here. And again, just to highlight, oxygen has a lone pair, so it's putting electrons into the system, and it's electron donating, and it's activating the ring. So this ring on the left is activated. This ring on the right is not deactivated. It's not activated. So the one left will react faster. So where will it add? You have two alpha positions and you have a beta position. Where will it want to add? Not the beta position. It has to be one of the alpha positions. All right. So relatively, this this spot is relatively para, while this alpha carbon is relatively ortho, and that's relatively para. Where will it want to add? I'm pretty sure it'll want to add to the closest alpha carbon. But in all honesty, it's probably going to be a racemic mixture as well. You can't really tell. Like the ratio is probably going to be like, I don't know, another 40%, 60%. Yeah. So if you had to pick one, pick the one that's relatively less sterically hindered. But this is probably going to be another racemic mixture. So the big ones are going to be these two on the right. So if your substituent on your naphthalene is already there and you're trying to react it, it's going to be on the alpha carbon on the same ring. All right. Now, let's go into certain group of reactions that I want to make note of. So the group of reactions that I want you to pay attention to. There you are. HNO3, H2SO4. That adds a nitro group to it. So this adds an NO2 to that aromatic ring. H2PDC. That changes that NO2 into NH3. NH2, I mean. There you go. 3. NaNO2 HCl 0 degrees Celsius. That changes it to N. Here, let me move these over here. Charge. This is where the charge is. There we go. Right? Those three usually pair to make a diazonium salt. All right, why is that relevant? Well, as you know, you can do a lot of things with diazonium salt. Okay, diazonium salts. Okay, so like from right here, all you have to do is HBF4, and you can replace it with a fluorine. I have a fluorobenzene. All right, but these reactions are usually coupled together. And this third one in particular, we just call that HONO. Oh no. All right. On synthesis, you are welcome to draw or just write HONO. All right. I will say that again. On synthesis, you're welcome to just write HONO. Okay. But on the reactions page where you have like 10 different reactions, you are expected to recognize this as HONO. I want to make that clear. That's a caveat. You are expected to know and recognize this right here. This is HONO. But that's why I'm making this video, because if you have H2PD and C and these grouped together, well, you kind of know that that's HONO. It's kind of almost just right there, right? If you see these three in particular, like, wait a minute, I know that looks like a diazonium salt reaction. I'm an organic chemist. Blah blah blah. All right. Next thing is some of the rules. So Friedel-Crafts reactions. Right here we have strong deactivator, weak deactivator. All right. If you were to react with Friedel-Crafts, what would you get? No reaction. All right. The moment you have one moderate deactivator or strong deactivator, there's going to be no reaction. All right. Because it's not strong enough to attract that Friedel-Crafts electrophile. Can't happen. Just no reaction. Right. Now, let's look at some various methods to make benzoic acid. So the first one's pretty common. So we can just oxidize something. So like you'll see these in various forms. So the first way is H2CrO4. That's what we know. That's our Jones's reaction. Or you could also see KMnO4. All right. Heat. All right. So if you were to have, let's say, any alkyl group, right, with a hydrogen, all right, this still has a hydrogen. So if you had a tert-butyl group there, it would not react. But still, if you, as long as that carbon that's attached to the benzene ring has a hydrogen, it can be oxidized. Okay. So the two ways you can see it are these. The one you know, or a possible curveball. I really hope you guys are picking up what I'm trying to pick up, or picking up what I'm trying to drop down. There's a good chance I might see this on the test. Are you gonna write that down? I really hope you write that down. But KMnO4 does the same thing. All right. These are interchangeable. Same thing. They're strong oxidizing agents. Now, if I were to try to get any kind of alkyl group, just Friedel-Crafts alkylation. Like, literally, this reaction will get you to a cumene right here. You might be thinking, wait a minute, isn't that a straight chain? How does it add an isopropyl group instead of a normal propyl group? Well, let's talk about it. Well, Friedel-Crafts alkylation, if you remember, has a carbocation rearrangement. So if that Cl leaves, and respectively, that would become AlCl 4. All right. That Cl leaves, well, you have a carbocation right here. Is a primary carbocation stable? No. It will rearrange. It'll do a hydride shift and form on the secondary carbon. All right, because it's more stable. And thus, if you have an electrophile in the secondary carbon, that is what's going to add to your aromatic ring. Something I do want to note. You can control that because if you want to add a chain, we'll just do acylation and the Wolff-Kishner reduction with hydrazine. Right? So hopefully you guys have been studying up some of these terms. The next term, or next reaction I want to get to is, your nucleophilic substitution. So like your electrophilic aromatic substitution, but the complete opposite, where it's more reactive with deactivated rings, right? And the caveats I want to make, or not the caveats, the rule that I want to lay down has to be para. So you see this X right here could be anything. This X could be a bromine, chlorine, or an iodine. It's a good leaving group, okay? While this group right here, it has to be a deactivating group. So on top of NO2, it could be benzonitrile or benzene sulfonic acid. Your strong deactivators, okay? So if I were to react this with NaOH, an extremely basic condition at a very high temperature, all right, how does it react? Well, essentially, let me right here. Whatever strong base you have will replace the halogen, okay? It'll replace the halogen. So NaOH in a solution, would be just OH minus. It would want to, there we go, attack this carbon, okay? And subsequently, let's draw out this nitro group. This is phase 1. Attack that, resonance over here, resonance over there. And then this over here. In a single step, you're going to have something that looks like this. And immediately, you're going to have this reverb. Okay, where you push it all on the deactivator and then it'll push right back and kick out that X. Okay, so You flow one way, and then immediately you flow the other way and kick out whatever halogen you have. And that will form this. That's the mechanism. Okay. Now, does it have to be OH? No. Because what other strong bases do we know? Well, OCH3. All right. If this was Na, OCH3, we just add an ether. All right. CH3. We just add an ether. And on top of that, that NO2 can eventually be reduced to NH2 and then form a diazonium salt. And we just remove that diazonium salt. All right. You guys remember that's, I think it's H2PO3. And that's a reaction that removes it. Yeah. And just it removes that nitrogen group essentially, but that's not what I'm doing here. I'm just trying to show you that it doesn't have to be OH. Now, I showed you NaOCH3. What's another strong base we know? Well, it's our good friend, our freakishly small strong base, NH2. So NaNH2, it also works. Pretty great, right? I know. So if I were trying to make this, all right, how the hell can that happen? Because remember, aniline cannot be nitrated or sulfonated. So how the hell do we get an NO2 and an aniline together? How the hell do we do that? Because if we added the nitro group first, well, it's going to add meta. So how the hell do we do this? So those are our two problems. NH2 cannot be nitrated. And NO2 is meta-directing. Meta-directing. Okay, so I'm going to show you two different strategies. So common strategy is, well, blocking the ability for NH2 to fuck up everything, essentially. So let's go ahead and just set it up. So the first reaction, let's just nitrate it, HNO3, H2SO4, NO2. All right, H2, EDC, NH2. All right, now this is the weird thing. We can react it with a Friedel-Crafts acylation. You might be thinking, wait, how can we do that? Because aniline, NH2, cannot react with the Lewis acids. And last I checked, well, Friedel-Crafts uses a Lewis acid. Well, let's see, LC3. Now, aniline cannot react with a Lewis acid because the aniline will react with it rather than the aromatic ring. But that's kind of what we're going for. It's going to look something like this. All right, that's kind of what we're going for. So if that's our compound, well, that still has a lone pair. I have an amide group. It's ortho pair directing. So if we were to nitrate again, HNO3, H2SO4, get something like this. All right, NO2. Now we can just remove that group with just simple HCl, H2O, H, and AOH. So this reaction right here that I showed you, it reverts this back into aniline. How do you do that? I mean, that's a whole lot of steps. Is there another way to do it? Yes, through nucleophilic substitution. So let's paint the picture again. Let's set up. Let's say we were to chlorinate it. Cl2, AlCl3. Okay. Chlorinate it. All right. This chlorine is orthopair directing. So if we were to nitrate it again, HNO3, H2SO4, we get two products. There's no regional selectivity. Two. It's the ortho compound. ClNO2. Right? You have to put both. Now you're thinking, well, how can we do that with synthesis? Well, all you have to do, filter, because we have many different techniques to filter certain compounds out. And that's all you have to do. You'd have to write both, but you just have to make sure you preface which one you're still going to be working with, because the other one will just be thrown out or done with whatever. All right. Okay. So now we have, I'm just going to redraw it. So if this is used, I'm just going to redraw it as this. Now you have ClNO2. Well, look at that. It kind of looks like up here, where we have an extremely deactivated ring and a leaving group that's para to the deactivator. What can we do here? Well, I'm going to go ahead and just erase this because you guys have the freedom to rewind the video and just go back. This is where the magic happens. NaNH2, 160 degrees Celsius, and then HCl. Yeah, that's right. Look at that. We do a nucleophilic substitution where that NH2 will just attack right here. Yeah, that's 3 steps. It's crazy. Will either way be accepted? Yes. So generally for your synthesis reactions, Dr. Berg will give you credit. So if you have a long convoluted pathway to get to the target molecule, if you're correct, you're correct. You will get credit. If it's too convoluted and there's like certain questionable reactions, like it's not exactly on the mark, because Dr. Berg's the one who usually grades the synthesis. He likes to call it style points. So what he's mainly saying is like, if you have to filter, like what I did down here, if you have to filter a whole bunch of things, that's not what he wants. And he might take off one for that. So you want to limit this. Can you do it? 100%. Of course you can still do it. It's inevitable. And you probably will have to at least once for the synthesis. For the shortest pathway possible that's on the key, it'll probably have at least one filtering, but you can't do like 5. 5, don't do. Like you do probably like 2, maybe even 3, but that's kind of it. All right. So with that being said, let's go ahead and just get into some reactions, just practice a little bit, because this is mainly pertaining to your guys' knowledge when you guys practice for the test and when you guys complete the problem set. All right. Okay. Here we have, a naphthalene and an activated group. Okay. An activating group. So where will it add? We're chlorinating it. So we know we want to add to one of the alpha carbons on the same ring because an activator. Well, the product. Okay. Now I'm looking back at it. I was right. So back here, I said as a racemic mixture, I think I saw somewhere that it'll go to the closest alpha carbon. Fix that. It does go to the closest alpha carbon. It can still react with the bottom one, but it'll react with the closest alpha carbon. That's where I forgot. Yeah. If OH is right there, if you're trying to react it, it's going to go to the closest alpha carbon on the same ring. So here, Cl is going to add right here. There you go. That's your reaction, or that's your answer. Now, Cl2 FeCl3. Okay. So if this is a tert-butyl group, so in actuality, let's wipe this out. This is what it'll look like in real life. Or use not in real life. It's still stick model. Tert-butyl group. Okay. Well, what do we do? Well, okay. We know that alkyl groups are ortho-pair directing, right? So if we're looking at this alkyl group, what are the ortho and pair positions? Right here, and right here. Okay. If we're looking at this alkyl group, the ortho pair positions are exactly the same. Ortho, ortho, pair. So it wants to add to these carbons no matter what. Well, we know from, our notes, if you have a position, a position that's pinched between 2 spots that are meta to each other, it will not react there. All right. So this spot is extremely unfavorable because you have 2 spots right here that are meta to each other. So this is kind of pinching in on that space. And I would much rather react with the open spots right here. Okay. So now you know that chlorine will want to add to either of these spots. Where will it add? Well, let's look at steric hindrance. A tert-butyl group is extremely big. Well, a methyl group is just a methyl group. So where will we want to add? Well, here, or here, it'll want to add to the bottom one. This is where chlorine wants to add because there's least steric hindrance. Okay, it is paired to the terbutyl group and it's ortho to the CH3 group, so it's still activated. All right, now let's go into here. You have a benzonitrile. All right, we know that this is going to be a, pardon me, strong deactivator. All right, so can Friedel-Crafts reactions, this is a Friedel-Crafts acylation, will it react with a strong deactivator? No, it will not. Okay, all right, I'm back. Okay, so for this one, we have first step, and we're nitrating something. So this is a carbonyl carbon. It's a ketone. It's acetophenone. Okay, this is a positively charged carbon. So we know that this is going to be a moderate deactivator. All right, that's a moderate deactivator. Well, let's look at the first reaction. HNO3. That is a nitration reaction. We will add a nitro group. And if we have a moderate deactivator, we know that that is going to be meta directing, NO2. The second one is right here. Look at that. What the hell is that reaction? So hopefully you guys are making your flashcards and you identify that right there. That's a Wolff-Kishner reduction. Kishner reduction. That's a Wolff-Kishner reduction. And he said before that if you know the general knowledge, you can easily get a C. But if you know the nitty-gritty, you can get an A. And this is the nitty-gritty stuff. Because you know, all right, what does a reduction reaction do? It removes bonds of atoms with hydrogens, and then oxidizing reactions, you increase carbon-oxygen bonds, all that stuff, blah, 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 blah. Okay, so Wolff-Kishner reduction, what will it reduce? Well, I want to make this side note. One of the things you have to keep in mind is that H2 PD on C, that's another one of her reduction reactions, right? We're removing oxygen bonds. It reduces everything. This, or hydrogenating our compound, removes all of them, or removes all the oxygen bonds. So it reduces everything. So the NO2 will be reduced to NH2, and this will be reduced to carbon, hydrogen, another CH3 group, compared to that oxygen group that was, or that carbonyl oxygen group that was there. That is what that would reduce to. So what's the point of the Wolff-Kishner reduction? Well, the Wolff-Kishner is selective for acyl groups right here. It'll only reduce that carbonyl carbon. So it'll leave that nitro group alone. So if we know that the first reaction gives us a nitro group, all right, the Wolff-Kishner reduction will now give us something like this, an ethyl group. Okay. And now the third step, that's really easy. Look, that's just H2CR4. That's another strong oxidizer reaction. We know this. Your alkyl group, it'll just be oxidized into a carboxylic acid. There's going to be NO2. And that's your answer. Okay. Now, let's look over here. What the hell is this? That's what you're probably thinking. Well, a lot of fun. Because again, this is the part where you're trying to poke at you if you know the concepts or not. Because you know, all right, ortho pair directing and deactivators have lone pairs and pull electron density or push electron density into the ring, while deactivators are partially positive or positively charged and pull electrons out of the ring. So if we were to blow that benzene up, just big close in, zoom in on that. Carbon, fluorine, fluorine, fluorine. Well, the fluorines are all partially negative, right? Because they're very electronegative atoms. Well, that carbon, that is extremely partially positively charged. So using your logic or your knowledge of OChem, what the hell does that mean? Well, this is going to be a deactivator. Partially positive charges or atoms that are next to the benzene rings deactivate the ring. This is going to be deactivated because it's pulling electron density away. So if it's deactivated, and carbons that are partially positively charged atoms are going to be moderate deactivators, and stuff with actual like positive charges are going to be more likely strong deactivators, but still they're meta directing. That's what I'm trying to say. Meta directing is going to be favored here. So if we were to brominate it, what would we make? Meta. Br. That's what we make. Okay. Let's go up here. Now, ooh, look at this. It's another reduction reaction. We're reducing it. Okay. H2 rainy nickel catalyst. What does that do? Well, I'm just going to redraw this group. C, and okay. That's all it is. So what that rainy nickel does is, well, it removes these, just puts hydrogens on there instead. That's all it does. So what does this do? CH2 and H2. I want to preface, it does not make aniline. The CH2 is still there. All right. Let's go to the next one. Br2H2. This is one of your radical reactions, if you remember. All right. What does that do? It adds a Br to a benzylic carbon. All right. So that carbon right there, I really hope you remember this, is benzylic. So that's benzylic, right? All right. That's benzylic. So we're going to add a Br there. That's all it is. That's all it is. Okay. Now for this one, what are we going to do? So 3 Cl groups, it's kind of deactivated, but only weakly. Don't worry. For to nitrate it, well, we know that Cl is ortho-pair directing. So we're going to look at this chlorine, ortho-para. This is ortho. This is para. If we were looking at, let's use green, this carbon, right? Both of its ortho groups are plugged up by the 2 chlorines, and para will be right here. Now let's look at this chlorine, all right? Let's look at those ortho-para groups. Ortho here, para there. So out of these 3 spots, which one's favored? Well, if 2 out of the 3 substituents really favor these 2 spots compared to this one, well, that's where your nitro group's going to add. And there. And you're thinking, why didn't I add it to the other side over here? Because if you did, this is an achiral molecule. Whichever way you add is the same thing. You can pancake flip that, and it's superimposable. Yeah, that's it. Bring back test 2 stuff from last semester. I'm glad you guys remember that, because I know you guys do, right? Yay. Okay. So the first reaction, well, look at that. NaOCH3. What the hell does that do? All right. Well, the only reaction I can think of is a nucleophilic substitution, because look, you have an extremely deactivating compound that's para to a leaving group, as in a halogen. So what is that first reaction? It just replaces that Cl. We talked about this. We are not new to this concept. NO2OCH3. That's what that first reaction does. It just replaces our leaving group, our Cl, with a better nucleophile. Now, H2PD-on-2, what does that do? Well, of course we know, it reduces NO2 to NH3. And look at this. Oh no. Yeah, there's coupled stuff. It's HONO. That's our HONO stuff. So if we know that the third reaction gives us this, OCH3. Oh, I meant to write 2. That's my bad. N. All right. That's our intermediate. And now we have that fourth one. That's just H3PO2. What does that do? It just removes the diazonomy salt. So now your final product is just going to be anisole. That's it. All right, last one. This is going to be a long one. Look at that. So let's take one step at a time. Fuming sulfuric acid. So I know that OH phenol, that's going to be a strong activator. So it's going to push for orthopara. But I really hope that you remember, well, phenol, when it's sulfonated, sulfur can only do para. Why is that? The steric hindrance. All right. Sulfur has a lot of oxygens connected to it. It does not want to be near other oxygens. So it's going to be pretty much just para. So the first one will only give us para. OHSO3H. Okay. Now 2. Now let's nitrate it. Okay. One sec. Okay, great. As nitrated. So if we know that, okay, phenol wants to do ortho pair and pair is already taken, and meta, or not meta, sulfur, or the sulfonic acid group wants to do meta, which is also here, those spots are very favored for the reaction. So when we add the second part, NO2, we're going to add that NO2 right here, NO2. Now its third part, H3O plus and heat. What that, all that does is remove the SO3H group. That's all it does. All right. So how do you remove that SO3H group? Just H3O plus and heat. It's really easy. Heat it up in an acidic solution. Now we get to the fun stuff. Look at this. Look at this pairing that we already saw. H2P and HONO on an NO2 group. So we know that just changes the NO2 group into an NH2 and then into a diazonium salt. All right, and then the last step right here, Ki, it just replaces the diazonium salt with iodine. Iodine, which that's all it is. Right. Yeah. All right. Okay. So let's take a look at this reaction. So we're trying to create or put a bromine there while we already have a disubstituted benzene with a dichloro group. How the hell do we add a bromine there? Because it is in the relatively meta position. And last I checked, chlorine's in ortho-para directing. So it'll want to add ortho-para here. Same thing with the other chlorine. The other chlorine right here would want to add here, here, and here, the same places. All right. And we know, well, this one's off limits because you can't really squeeze something in there. So if those are the only spots I want to add, how the hell do we add Br? Well, it's pretty tricky to think about it. Well, when in doubt, I usually try to put a nitro group somewhere and see if, all right, if a nitro group, or okay, the reason why I like to put nitro groups on places, right? If I don't immediately know, like, okay, this is what I should do. I think you should do this, doing that. If I'm ever in doubt, I put a nitro group there because, okay, nitro group, if you leave it as it is, it's a strong deactivator and it pushes things meta. But that same nitro group, you can make into an aniline, make it into a very strong activator. All right, it's a very strong activator. If you remember, strong activators, if you strong activators. And not only that, if you have a strong activator, you can also change the strong activator to a diazonium salt. So essentially, wherever that nitro and aniline group were, you can replace it with literally anything, with an iodine, halogen, CN. You can remove it with H3PO2, or you can hydrolyze it into an OH. You can do a lot of things with it. So let's try that thinking out. So if I were to nitrate it, all right, HNO3, H2SO4. How do I make something like this? Cl. With what I have right now, can I put a bromine on there? And that ring is extremely deactivated, right? And if I were to add the bromine, well, the bromine would just add here because it's still ortho-para to the chlorine. And not only that, but it's now meta to the meta director. So that spot's extremely favored. So we don't really want to do that. So let's take it to the next step. Let's H2 PD on C. NH2 Cl Cl. Now we have an extremely strong activator. And remember, whatever's higher on the list is the directing group now. So if NH2 is the highest on the list, it is now the director group. So now it will like to put things that are ortho-para to it. Ortho, para. This ortho and that para groups are already taken, but now it's favoring that ortho group. Well, look at that. That's where we want to add the bromine. You can just do Br2. Might be thinking, Patrick, why the hell are you not putting FeBr3? Well, you can, but also remember, NH2 reacts with Lewis acids. But strong activators don't really need a Lewis acid catalyst because it's that activated. It'll put a Br in ortho-para position just by itself, right? So if you had a normal, like phenol, for example, all right, if you were to do Br2, That's all you need, and it'll add a Br to the ortho pair position. If you did FeBr3, it'll add Brs to every position, every ortho, every pair position. Okay, that's the thing with strong activators. So for NH2, I don't really want to react it with fluid acid, but all I need is just a Br2. That'll work. Now, could you have realized that? Yeah. Could you have just like left it as it is and not think about it and still get points? Yeah. Is that a good thing? Fuck yeah, it is. Who cares? Who the fuck cares? As long as you get it. Okay. Now you're here. Now you have what you need. You just need to get rid of the aniline group or the NH2 group. Can you get rid of NH2? Fuck yeah, you can. Oh no. Right? And then all you have to do, H3PO2. Now you have your target molecule. Yay. Good job. It's supposed to be BR. All right. I'm done with this. So I hope this video helps with certain considerations for various reactions. And yeah.